As all of you know, Professor Subhash Chaturvedi needs no introduction. So Professor Chaturvedi is stalwart among Indian physicists working in the fields of mathematical physics, quantum optics, and quantum information. He was associated with the University of Hyderabad for many years. At present, he is visiting professor at IISER Bhopal, and he is fellow of many national academies. He has several recognitions to his credit. So Professor Chaturvedi's research interests lie in the areas of phase-space description of quantum systems, geometric phases, quantum and classical optics, non-equilibrium statistical mechanics, and quantum information and computation. He has made several important contributions towards these areas. Well, Professor Chaturvedi is very well-known inspiration to my generation of physicists. And for the benefit of young students, that we again say that I've known him for more than 2 decades, during which he has made several visits to our region. And so today, very warm welcome to you again, sir. And Professor Chaturvedi will be speaking. The title of his talk today is an overview of phase-space descriptions of discrete and continuous variable quantum systems. So, Subhash, the floor is yours.
So you can hear me?
Yeah, we can hear you.
All right,
yes.
all right. So I will start with some acknowledgements to people from whom I have learned a great deal insofar as this subject of phase-space description of quantum systems is concerned. I have spoken about this topic many times earlier. I have tried to sort of add a few new aspects which I would like to focus on or work on at this stage in my life, hopefully with some success. And that is what I would like to highlight and outline to you. This, as I said, I have learned a great deal from people like very, very gifted people like Professor Mukunda, Simon, Arvind, Professor Agarwal, Marmo, Elisa Ercolesi, Ingmar Bengtsson, Marcus Appleby, Ajit Iqbal Singh, Shivashish Ghosh, and K.R. Parsarthi. So what I am presenting here is a sort of an overview of the efforts that we have made in the direction of coming up or designing phase-space descriptions of finite state systems as well as continuous, inspired from the phase-space description of continuous variable systems. So I will start from scratch. Having been a teacher all my life, I have this bad habit of not assuming anything on the part of the audience. So I will start from classical phase space because some of the notions that we would consider to be desirable in quantum phase space descriptions are inherent to classical phase spaces. And here, as you know, that if you're given the configuration space of a particle, there is a procedure, there's a mathematical procedure to construct out of the configuration space its phase space. Most of the time, I will be confining myself to a particle described with a single Cartesian degree of freedom. So the configuration space is just a real line, Q extending from minus infinity to plus infinity, and it's what is called the cotangent bundle is simply R2 or a two-dimensional plane, which we can picture in the usual Cartesian fashion as shown in the figure. And a point in this phase space will be denoted by sigma. Of course, you must appreciate that the lines have been drawn orthogonal to each other just for convenience. There is no notion of orthogonality in the phase space. However, there is a notion of a product which is called the symplectic product, and it's an important one. So if you take 2 points, sigma and sigma prime, then their symplectic product is defined, expressed in terms of the coordinates and momenta as shown in this slide. Now, I will sort of rush through some of the notions which I would use later on in my talk, and therefore I feel that it is important that I straighten them out right at the outset. So I would speak of isotropic lines, or sort of simply stated, straight lines through the origin. And these are defined through a point sigma is given by set of all sigma prime, all points sigma prime, such that they have a zero symplectic product. And this is the definition of an isotropic line, which I would also refer to as straight line through the origin. Now, there are certain important operations which you can perform on classical phase space, and later on we would look at their analogs in the quantum situation. And these are, first of all, displacements. So you can displace a point, phase point, by the amount sigma naught. This is a sort of usual translational group in a two-dimensional Euclidean space. Then there are another set of important transformations which constitute a group, and that is called the symplectic group. And this is the set of transformations which leave the symplectic product unchanged. And this is an important symplectic group. It maps the phase space onto phase space. As I said, later on, all these notions will acquire meaning in the context of quantum phase spaces as well. Now, there's another notion which we would need, which is called the foliation or striation of a phase space. So if you are given an isotropic line, that is a line through the origin, and then you draw a set of lines parallel to it, and this set of lines parallel to the isotropic line then give you a decomposition of the entire phase space in this set of straight lines parallel to this isotropic line. So each straight line through the origin then determines a decomposition of the phase space into, into straight lines, which for brevity would be referred to as a foliation or a striation. Now, again, if you are given in the classical context, if you are given a phase space distribution, FQP, which is a pointwise positive function of its arguments, then, and if you integrate, if you choose any foliation and integrate this function along the lines, then what you get is a probability distribution, and this would be referred to later as the marginals property. So these are some of the features of classical phase space which one has to bear in mind, because when we move to quantum case, we would like to try and ensure that as many of these properties are also valid, are also satisfied in our quantum description. Now, as you all know, that in the from the point of view of historical development of quantum mechanics, the passage to quantum mechanics proceeded through replacement of the coordinates q and the momenta p by operators q hat and p hat on a Hilbert space H, and replacing the Poisson bracket of the Hamiltonian mechanics or the phase space description of particulate mechanics by the commutator. So this is the sort of route to this is a route to quantization of a given particulate system, and is an important, of course, later on, there are many other routes to quantization that developed, but this was the earliest way of arriving at a quantum description of a classical mechanics, classical particulate system. Now one may ask the question that if Q and P go to, now of course we have Q and P as operators, and I've listed here, I will not go through them, several operators which are related to Q hat and P hat, and I'm sure that the audience that I have must be familiar with these properties, the position operator, properties of its and its eigenfunctions, which are continuous, labeled by a continuous variable Q. Then momentum operator P hat is and its eigenstates are related to the coordinate eigenstates by a Fourier transform. And then, of course, you can construct linear combinations of Q's and P's to arrive at operators A hat and A dagger hat, creation and annihilation operators, then quadratic operators, number operators, their eigenstates, and I'm sure that all of you are familiar with these notions which are associated with quantum mechanics of a particle with one single Cartesian degree of freedom. So what is more important in this context of phase-space description are these while operators, which are exponentials of Q hats and P hats, and their properties are listed here, and their action on coordinate and momentum eigenstates are here, given here. I have included them for completeness because these are the definitions which we will take over in when we move to a scenario different from the Cartesian degrees of freedom to discrete variable systems, where we have no classical mechanics or classical analog of a classical phase space. So this is just, I've included them for completeness. So important for us, is an operator which is given here, which is e to the I p q hat and minus I q p hat. Properties of the displacement operators are given here. And what is important for us to remember is that these operators constitute a set of unitary operators, which are trace orthogonal, and their composition property is given here, and they give you a representation of the Heisenberg while group. Now, again, a brief recapitulation of ordering prescriptions leading to phase-space descriptions in quantum mechanics. And this was the first effort in this direction. And this was due to Weil. And where the question that you ask is that Q goes to Q hat, P goes to P hat. What happens to an arbitrary function of Q and P? How do I construct the corresponding phase space? How do I associate with an operator with a phase space function, an operator on the Hilbert space, and vice versa? So this was the Weil rule given. And Weil was a very great mathematician. Cleverly, he chose the exponential function in order to specify this rule, because this exponential function then appears in, suppose I start with a phase space function FQP, and I look at its Fourier transform, then I would have such an exponential function appearing in the process of Fourier transformation. And then I have a simple rule to associate with it a corresponding operator. It just consists of replacing the exponential by this operator here. And then using the trace orthogonality of the displacement operators that appear therein, one is able to arrive at a rule which allows you to associate with an operator a phase space function and vice versa. The rules are given here. We are not going to use them very much, but I just wanted to tell you that this is the idea underlying the development of phase-space description of quantum systems through ordering prescriptions. Now, this is one of the prescriptions. There can be many others, and I will just list here some other rules which allow you to construct different prescriptions for associating phase-space functions with operators and operators with phase-space functions. The least we would require in this correspondence is that a real function of Q and P should go to a Hermitian operator and vice versa. And these rules that I'm going to talk about, all of them fulfill this property. Now, the next, another very important ordering prescription is the normal ordering prescription, in which you rewrite the exponential, which is in terms of classical variables, in a factored form as given in this slide. And then you elevate the classical functions of Q and P to operators in this manner. And this is called the normal ordering prescription. And it amounts to replacing, when you do the Fourier transform, it amounts to replacing the exponential function that appears in the Fourier transform by the displacement operator times a factor here. Now, the effect of this extra factor that comes in is that, unlike the description which I talked about earlier, there was the same operator which allowed you to go from phase-space functions to corresponding operators and vice versa. In contrast, here you have two sets of operators which take you, for example, this operator phi hat, which is needed to go from a phase-space function to its operator, and in order to go from the phase-space function to its from operator to its phase-space function, you need a different operator Q hat. So in that sense, you don't have the same operator which is used for going from the phase-space functions to the corresponding operators and returning from operators to the corresponding phase-space functions. So this is the traditional way of arriving at phase-space descriptions, and the three prescriptions are known as symmetric ordering, normal ordering, and anti-normal ordering. Each of them have their own special properties, but let me not spend too much time on this aspect of phase-space functions, which might be all familiar to you, and I restrict myself only to sort of giving you the relative merits and demerits of these three prescriptions. So all the three prescriptions associate real phase-space functions with Hermitian operators, and conversely, real phase-space functions with Hermitian operators. In the normal ordering prescription, the phase-space function, the Q's function associated with a positive operator is pointwise positive. The converse is not true in general. In the anti-normally ordered prescription, the operator associated with a positive space-space function is a positive operator. The converse is not in general true. But the symmetric ordering prescription, which I would hereafter refer to as the Wigner-Weil description, has neither of these properties, much in contrast to what you would imagine that it would have both the properties. This is not true anymore. Neither of these properties are in general true for the Weil or the symmetric ordering.
we lost the presenter, right?
Yeah, I think his connection got disconnected. Okay. Yeah, Professor Chaturvedi, maybe you can share the screen again. And you are muted.
All right, am I unmuted now?
Yeah, you are unmuted. You can share the screen again. I think.
Now, what do I do to share the screen?
You have
Go
that green share screen button at the top of your application, if I remember.
Share, stop share. So I should, there's a, okay, screen. Now screen broadcast, eh?
Yes.
Okay, just 1 second, let me seek help. Sorry about this.
Yeah, no.
Are Nikita? Through the traditional procedure of passing from classical, phase-based functions, classic functions of Q and P to their operators on the Hilbert space and vice versa. Remember that these are prescriptions and there can be many such prescriptions, but these 3 prescriptions in particular have been of particular use in quantum mechanics and quantum optics. And I have, of course, listed their usefulness in this context, and you can look at, to save time, I will now pass on to something which you may not be very familiar with. So now I focus on hereafter, I only focus on Wigner phase-based description because of the fact that, as I've said, that this is the only phase-based description which is autonomous in the sense that a single set of operators associated with each phase point, each point Q and P allow you to pass from functions on phase space to the corresponding operators and vice versa. And certain properties I will now, so the entire content of Wigner-Weil description is captured by these phase point operators. And I will now tell you what are their properties, because these are the ones we would try and in situations which are not, which are unfamiliar, which are new, for instance, discrete phase spaces, these are the properties that we would like to carry over and in the new setting. So these phase point operators are trace orthogonal Hermitian operators, and they have this property that if you add them along a line in phase space, then they yield a projector. This is the analog of the marginals property that I talked about in the context of classical phase space distributions. Then projectors belonging to the same foliation are orthogonal to each other. For instance, if you look at the lines which are parallel to the coordinate axes, and then each of these lines will be associated with, if you were to average the phase point operator along such a line, then they will give you a projector onto the momentum eigenstates. And you have a family of such orthogonal in the delta function sense set of operators. And what is also worth noticing is that the projection operators belonging to different foliations are mutually unbiased, in the sense that if you take the, for instance, take the operators, the projection operator onto coordinate eigenstates, and take the projection operator onto momentum eigenstates, then their modulus of this trace of the product of these two projection operators is a constant, independent of Q and P. And this is the term which is used, the mutually unbiased is the term that is used in this context. So two sets of, we would later talk about mutually unbiased bases. So mutually unbiasedness means that you have two sets of orthogonal, orthonormal bases, such that the product of one with the overlap, modulus of the overlap of a vector from one basis with another basis from the other orthonormal basis is a constant. Now the displacements by an amount sigma 0 in the classical phase space will be implemented at the quantum level by these displacement operators. Then we have the symplectic transformations that map the phase space to phase space, and these would now be implemented by unitary operators, which in the context of single mode or two mode degrees of freedom are referred to as squeezing operators. These are the operators that will be required at the Hilbert space level. Then the phase point operators are covariant under symplectic transformations. Now, one important feature of this development of the phase space descriptions is that they permit you to define what are called Gaussian states. So a Gaussian state is one for which rho hat, those density operators for which the corresponding Wigner function, or for that matter, the Q function or the phi function is a Gaussian, are referred to as Gaussian states. And as you know, there has been an important contribution from our country by Professor Simon on in the context of entanglement between single mode, bipartite single mode Gaussian states. And that's why notion of Gaussian states is very important, both from the point of view of entanglement, as well as from the point of view of quantum communication. So I have included this. The significance of Gaussian states is that they are completely parameterized by the variance matrix. So you have a whole family of states which are completely specified by the variance matrix. And as you might have learned in some other lectures, particularly on entanglement in continuous variable systems, that the variance matrix, not every Gaussian corresponds to a positive operator, but there are restrictions on this variance matrix arising from the fact that the Gaussian must be associated with a positive operator. So this is some sort of a very quick review of something that one may have come across earlier in the context of phase space description of quantum systems. Now I move on to another approach to developing Wigner functions. I'll focus entirely on Wigner functions, which, as we will see, will be useful in the context when we move away from the context of phase spaces, which are the Euclidean plane. And this is a work which is done in collaboration with several others, which is given here. And here the idea is to start with the traciality property of the Wigner description. Namely, if you take the trace of a product of two operators then the result. So if I take the product of trace of two operators, of course, I can bring in phase space description of operators by considering their mixed matrix elements sandwiched between Q and P. Now I look at the trace of a product of two operators, then I find that while the left-hand side is symmetric under B and A, but the right-hand side is not symmetric under the interchange of the two phase space functions that appear in the integral. We can make this symmetric. We call it a Dirac-inspired approach because this is the kind of thing which Dirac would have done had he looked at this question of Wigner functions. So we can restore the symmetry by introducing a kernel, and this is the next step. I'm just giving you an overview of what is the idea involved rather than worry about the details, and where the objects appearing in this integral are given here. So once you've got it in this form, then what we do is to define a square root of this kernel that comes in here. Now we have got, after introducing this kernel, we have got the manifest symmetry of the left-hand side also appears on the right-hand side. And now if I define a square root of this kernel that appears in here, then I can rewrite the trace of a product of two operators in terms of two phase space functions, which are given here. And this, in fact, one can check, compute the square root of the operator that I have written down earlier, and you find that this is exactly the definition of a Wigner function that Wigner originally proposed. So here, the whole procedure of arriving at Wigner functions becomes completely algebraic in the sense that you introduce this kernel and then find the symmetric square root of this kernel, and then you have the Wigner description available to you. And this can also be used in discrete variable systems, as we will see. Now, I just want to bring to your attention the fact that the situations where the configuration space is not Rn, but is more complicated, or is a group manifold of a compact Lie group, then these have been discussed in a set of papers which are referred to here. I will speak no more about this. Now we come to phase space description of finite state quantum systems, and we will assume that D is P to the n prime power, because there is a phase space description developed by Gibbons and Wouters in this context of finite state quantum systems for the case when D is equal to P to the n, because in for P to the n dimension, we have a finite field available, and therefore we would have a phase space which would inherit all the properties, familiar properties of the phase space that we had in the continuum case. However, when D is finite, there are two possibilities: whether you allow the coordinates and momenta to take values in the field F P to the n, or Q and P to take values in the ring Z P to the n. Now, just to remind you, Fpn, in the context of fields, you can multiply two elements, and every non-zero element in the context of a field will also have a multiplicative inverse, where in the ring that may not be so. And we will see that whether you choose the field case or the ring case, the corresponding phase space descriptions are very, very different, because the structure of the phase space is very different in the two cases. The first one was examined in detailed by Gibbons et al. And it stems from ideas developed by Wouters, and it led to the notion of quantum nets, which I will explain in a minute. And then, of course, for the same situation, we can also use the square root approach in order to arrive at the description, Wigner phase space description for the finite state case. Now, just to give you some ideas about the structure of the phase space, when Q is in a field FD, again here all the properties that you have, geometrical properties of the phase space, the lines, etc., and the points, they are very similar to what one has in the continuum. 2 points define line. Parallel lines have no points in common. Any two non-parallel lines intersect at exactly 1 point. And as a result, the phase space has exactly d+1 isotropic line, straight lines through the origin. Each isotropic line gives rise to d-1 lines parallel to it. So you have a decomposition of the phase space consisting of d squared points into exactly d lines, and each line contains d points. And for example, I've shown you the phase space now, which will be a discrete lattice, and each point is labeled by Q and P, and Q and P take values in the field F3. And here I have drawn the isotropic lines in the first set of four figures, and then the corresponding parallel lines in the next line. However, when we go to the ring case, the situation is very different. Number of isotropic lines is much larger, much more than what we have in the field case, because now those geometrical properties that we had earlier, that isotropic lines, two lines through the origin intersect only at 1 point, are no longer valid. And as a result, the structure of the lattice, the geometrical properties of the phase space lattice are very different. And all these details I've tried to summarize here because they would be, I would comment on them a little later. These are the features that give rise to differences in the phase space description in the field case vis-a-vis the ring case. Now, in the quantum net construction of Wouters, what one finds is that you have to if you assign you have to assign projectors to these isotropic lines and assign projectors to the lines parallel to them, consistent with translational invariance. Then you find that these projectors turn out to be automatically mutually unbiased, in the sense that you take one foliation and then the projectors associated with that foliation and the projectors associated with another foliation give rise to two orthonormal bases, such that the modulus of the scalar product of one vector from one basis with another one is just a constant, and the constant is 1 over square root of d. And here, for example, in the context of so you can see that the construction, the quantum net construction of phase space description requires the availability of mutually unbiased bases, because these are the ones that you will assign to the foliations, and the vectors in each of these mutually unbiased bases to the lines in each foliation. So you have to have these available. And then once you've got this, then you can associate a phase point operator W sigma, which is obtained by by this formula here. That is, you have a line lambda and the associated projector here, and you sum over all projectors associated with, so sum over lambda, all sigmas lying on that lambda minus the identity operator. Then you get a phase point operator which has the property, which is Hermitian and has the trace orthogonality properties that are required in order to proceed to Wigner description. So these phase point operators have this. So just to summarize, you have a quantum net in which you assign projectors to each foliation in a certain manner, drawn from mutually unbiased bases, and then you have construct the corresponding phase point operators, and these then give you the Wigner description. These are the operators that would be needed to pass from a function of Q and P to an operator and the other way around. Now, there are many possible ways of doing this assignment. And in fact, one can calculate that how many distinct prescriptions that you can have on the face of it according to this procedure. And you find that there are d into d minus 1 of defining sets of phase point operators, and therefore that many Wigner distributions. So unlike in the continuum case where you had only one Wigner distribution, here in the discrete case, you have a Wigner description which has all the properties that you desire of a Wigner function, but then there are very many such possible descriptions possible. Now you can ask the question, how many of these various possibilities of Wigner distributions are spectrally distinct? That is to say, you can ask the question, if you look at, of course, the phase point operator at the origin, then all the other phase point operators, if you fix that, then all the other phase point operators, since they are related to it by displacement operators, will have the same eigenvalues. So you ask the question, how many distinct Wigner functions I have which are spectrally distinct in the sense that the eigenvalues of the Wigner phase point operators are different. And this question was addressed in a work by Marcus Appleby, Bengtson, and Chaturvedi. And fortunately, the initials combine to make A, B, C, like alpha, beta, gamma paper. Anyway, it's not that the paper is not of that caliber, but certainly answers this question as to how many distinct possibilities the Wigner descriptions are available in the context of Wouter's quantum net construction for the case when D is an odd prime. Now, for other prime powers, even case, these questions are still open, and anyone who is interested in discrete mathematics may try and work on these questions, on these problems. Now, similar in the context of, now I will outline the algebraic approach based on the square root. And what one finds is that just taking the square root of that kernel in the discrete case, what one finds is that you have a phase point operator which has this structure, very similar to what one has in the continuum case, except that there are, because of the process of square root, there are undetermined signs which appear. all these operators will form a trace orthogonal set of unitary operators. The only property that now one has to enforce is the marginals property, that is, the sum of the phase point operators must yield a projector. And this requirement then gives a condition on these signs, and the condition is given here, and one can ask, what are the various possible solutions of this for the signs? It turns out in the ring case that if D is odd, then there's only one solution, and the Wigner function that you get is the one that would descend, is the direct descendant of the Wigner function in the continuum. That is, the phase point operator at the origin is a parity operator. So in the ring case, what you find is that when the D is odd, then you have a faithfully the same kind of a Wigner function as you have in the context of in the continuum case. Now, some comments. My time is nearly complete, and I would like to leave some time for discussions because I've tried to compress quite a lot of things that I've been involved in this lecture, and I'm sure that there will be many questions in this context. Now, as you all know, that given a density operator, you need at least d squared minus 1 projectors in order to tomographically reconstruct the quantum state. The quantum net approach of Waters provides exactly the right number of projection operators, and which are of course also mutually unbiased, and then that's it. In the ring case, however, because of the different structure of the geometry of the phase space, you have many more projectors than d squared minus 1. And one may ask if there's a constructive procedure to select out of these projectors an optimal set for tomographic purposes. That is, can one select out from these more than d squared minus 1 projection operators a subset which is just required for tomographic reconstruction of the quantum state? And this question was addressed and answered, among other things, in this paper with K.R. Parsati, Shubhashish Ghosh, and Ajit Palsi that appeared in reviews in mathematical physics. Now, let me just make two comments on the problems associated with these finite, the phase space description of finite quantum states that are of interest to me and which I would like to pursue, and maybe with the help of one of the students who may turn out to be interested, whom I might have made interested in this topic. And one is the definition of Gaussian states in the context of finite state quantum systems. You know, this question of Gaussian states, as I tried to indicate, play a very important role in continuous variable systems. And one may like to see what if one can define similar kind of states in the quantum case. Now, of course, Gaussian distribution, there is no known, as far as I know, analog for Gaussian distribution on discrete variables. So one has to somehow figure out what is the definition of Gaussian states, because then these would presumably parameterize by something analogous to a variance matrix or some limited number of parameters, and it might be possible to answer questions pertaining to entanglement of Gaussian states in D1 cross D2 systems for all values of D1 and D2 in the context of finite state quantum systems. I don't know whether this is a question which occurred to me. I have made some progress in the direction of defining Gaussian states, but there are still many mathematical questions which need to be addressed. And another intriguing feature which I find is that a recent work of Wouters and Brash, which is deals with Specken's work on epistemically restricted classical theory on discrete systems based on discrete phase space. And I would like to see what the question that is addressed in this paper, what is new or what is different that arises when one looks at the same question from the perspective of phase spaces based on the ring ZD rather than the field FD. So I think with this, I will close my talk and address any questions that you might have.
Yeah, thank you, Subhash, for the very clear talk. And now it is open for questions, comments.
How do I go back to my?
I have one question, clarification.
Can you see me?
I
Start video.
Yes. Yes, exactly. You can see. Yes.
Yes.
Yeah. So now the question can be asked. Yes.
Okay. Thank you for your talk. This is a clarification question. Am I correct that in case of discrete variables like spin, we will see spots in the phase space instead of smooth surface in case of continuous variables like x and p?
So can you repeat the question?
Am I correct that in case of discrete variables like spin,
yes, so
I
referring to
will see spots.
System?
Sorry.
You're referring to two-level systems then?
Yes, two-level system.
Yes.
I will see spots in the phase space.
That's correct, because the function, the phase space function, the Wigner function will now be defined on the points in this lattice.
Yeah. So instead of smooth surface, in case of continuous variables x and p. Thank you. Thank you.
That's correct.
Okay, other questions or comments? Anything in the chat box? Well, okay, till the time we have one. So although we are running out, but Subhash, I was very interested in your application in the state tomography, that part which you briefly alluded to. So very quickly, can you just give a brief description of what exactly you did then?
Now here, what happens is that you get in the ring case, if you're dealing with the phase space description on the ring ZD, then you have many more lines, many more isotropic lines, and the projectors associated with them. And one very intriguing, this is just not one thing which I forgot to mention. Very interesting observation, or what you find in these phase space descriptions, whether it is the ring or the finite field, is that overlap between two lines in the phase space is exactly equal to the trace of the product of the corresponding projectors. Very intriguing property. One is a completely geometrical, for example, in the context of Wouters' description, the two isotropic lines only intersect at the origin. So what you find is that the overlap between the corresponding projectors is given by 1 by d, where d is the number of points on that line. Whereas in the ring case, two isotropic lines can intersect in more than 1 point. And then you find that the overlap between the corresponding projectors is exactly given by the number of points where they cross divided by the number of points on each line. Very interesting. One purely geometrical aspect and the other a quantum mechanical average. Now, in answer to your question, in this, as I said, because of the geometry of the phase space, you have many more projectors than are actually required for tomographic reconstruction. In the ring case, you have exactly d²-1 projectors. Here you have many more. So can one, of course, you would say that if you use them all, they would certainly be able to reconstruct the state, but can you select out of it an optimal basis? Can you select out of them d²-1 projectors, which will allow you to reconstruct the state? And a procedure for doing that is given in that paper, which I referred to.
Okay, thank you very much. And thank you once again, Professor Subhash Chaturvedi, for this very nice